Okay, we're ready. Unit 2.8, all about inverse functions. I've already mentioned inverse functions to you guys when we were doing the compositions. Remember I said that one of the few times where the composition is commutative is if you're working with inverses, because f of g of x and g of f of x will both give you the result x, and that's because inverses cancel each other. Well, this whole lesson, today and tomorrow more than likely, is devoted to understanding inverse functions. Start with some basic vocabulary. A relation is a set of ordered pairs. So some x's and some y's, okay? A function is a very special relation where for every x, there's exactly one y. That's what it means to be a function, f of x, g of x. That means every x that you put in, a unique y comes out. For every x, there's exactly one y. If a function, f, is a set of ordered pairs, x, y, then the inverse is the set of ordered pairs, y, x. Okay. Essentially, an inverse switches boop, boop, x's and y's. That's what it does. You switch your x's and your y's. And we'll actually do that algebraically to solve for the equations of our inverse functions. But anyway, something really, really special happens when you have a function, call it f, whatever, and its inverse is also a function. Because, you know, not every time you switch x and y's is it going to produce a function. But if it does also produce a function, then what you could say is f is 1 to 1. That means for every x, there's exactly one y, and for every y, there's exactly one x. That's what 1 to 1 means. A function f is a 1 to 1 function if you've got an a and a b in the domain, and a doesn't equal b. So, you know, we've got like a 1 and a 5 or something like that. If you've got two inputs on a 1 to 1 function that are not equal, it guarantees you have not equal outputs as well. It's just a neat idea. It says different values of the domain will always get you different values of the range. So a minute ago I told you that it switches x's and y's. So if you switch all the x's and the y's, that means you've also switched the domain and the range. And this is a really important concept for inverse functions. Basically it says the domain of a function is the range of its inverse. And vice versa. The range of a function is the domain of its inverse. Literally, all of the x's and y's switch places. Graphically, switching x and y does this to a picture. Turns it on its side. That's what it looks like. Now, we don't do rotations in algebras. We can do rotations in trigonometry, but we don't do them in algebra. And one of the reasons why we don't is because there's a good chance that it'll develop something that is a non-function. For example, just a piece of scrap paper here. Here's a function. I recognize it as a function because it passes the vertical line test, right? Its inverse looks like this, which is not a function. So what that tells us is that this is not 1 to 1. Yes, it's a function, but its inverse is not. And one of the major reasons why we don't do rotations in algebras is because it could produce non-functions. Cool? We'll talk about this maybe tomorrow, maybe the end of today. We'll see. So what we have here are some maps. These are just relation maps. And they're showing you x's being turned into y's. And we say they point to, you can say they map to, and it says just justify each mapping with an observation. Here we've got our domain is 1, 2, 3. We've got our range is 4, 5, 6. It says this function is 1 to 1. And we've just been told to justify that. So how do we do that? What is the definition of 1 to 1? For every x, there's exactly one y. So check out your x's. They all have a unique arrow. And each of those arrows points to a y. None of those y's repeat. None of these x's repeat. So what makes this 1 to 1 is we could say for every x, there's exactly one y, and for every y, there's exactly one x. Let's just say 1y to save space. So as long as no x has two arrows, and as long as no y has two arrows that point at it, you're guaranteed to have something that is 1-to-1. This is a function, and its inverse is a function. For every x, there's exactly 1y, and for every y, there's exactly 1x. So for this one, this is still a function. This is a function. For every x, there's exactly 1y. But why is it not 1-to-1? What y value is causing us a problem? 4 is a problem. This y value has two different x's that point at it. That means, if I were to turn this graph on its side, I'd have a y value, say this line right here. See how this y value hits the graph twice? If I turn it on its side, this horizontal line that I'm tracing becomes a vertical line that can hit my graph twice, and now it's no longer a function because the inverse fails the vertical line test. So this is not a function, excuse me, this is not a 1-to-1 function because it is not true that for every y there's exactly 1x. Right here. For this y, there is more than 1x. So yes, this relation is a function, but its inverse is not. Therefore, it is not 1-to-1. Why isn't this a function? What x? You can all shout it out. 1, yeah. This is not a function because for this x, there's more than one y. Okay, bonus question 4. Is the inverse of this relation a function? Landon says yes. He's right. Because for every y, there is exactly one x. Y equals 4 has a single x. Y equals 5 has a single x. Y equals 6 has a single x. So this relation is not a function, but its inverse is. I've already said this, but if the graph of a function is known, you can use the horizontal line test to determine whether or not it is 1-to-1. I'm going to keep throwing this parabola up here. This parabola, and all parabolas, is a function. It passes the vertical line test. There's not a single vertical line I could draw that would hit this in more than one place. However, this horizontal line and many others like it hit this graph twice. What that means is, for that y value, there's more than one x. You see that graph fails the vertical line test. Because for this vertical line, there's 2 hits. Yes, sir?
Does that mean that all linear equations are 1-to-1?
Oh, no, all linear equations, as long as they're not horizontal lines, are 1-to-1. But what it tells you is every quadratic is not 1-to-1, but there's a ton of graphs that are still 1-to-1, like the parent x cubed, that's 1-to-1. Because it's not horizontal in more than one point. And also the reciprocal function, we did these already, right? For rational functions. That's 1-to-1. So there's lots of graphs that are 1-to-1. Yeah, but a lot of polynomials are not 1-to-1 because they look like pieces of spaghetti. So a lot of polynomials are not. I would even wager to say at most aren't. But Now, there's still a lot of graphs out there that are one-to-one though, but yeah, linear equations are like almost always one-to-one. As long as themselves are not horizontal. Or vertical, because if it's vertical, it's not a function, right? If a horizontal line intersects the graph of a function in at most one point, then the graph is one-to-one, meaning you passed the horizontal line test. Great. So you've got some properties of inverse functions. Graphs of inverse functions are reflections in or over a very specific line. I told you it switches x and y, right? Well, that is the same as being reflected over the line y equals x, which is something you should have done way back in geometry. You should have reflected pictures over the line y equals x, and you should have done it in Algebra 2 as well, switching x and y, plotting some dots, maybe finding the equations of functions and their inverses. So for this picture, what we have is a graph, which is a function. Oh, it's a cubic, like I just said to Lana. Here we go, we have a cubic. And here's its inverse. And if you were to turn the page, you could see that these things are perfect reflections over the line y equals x. Looks like a mirror, right? So given a function f, the inverse for that function looks like this. That superscript of -1, that is not an exponent. If it's written after the name of the function, but before the variable of the function, it's not an exponent, it's a superscript. This says f inverse of x. Please don't say f -1, please don't say f to the -1. It's f inverse. The domain of a function will always be the same as the range of the inverse. Whereas the range of a function will always be the same as the domain of its inverse. And I don't know if it's going to come up later in the notes or not, but if you ever need to plot and graph an inverse, all you have to do is identify some pretty points on that graph, identify those, and switch their x and y. This one was at 1, 3. Its reflection is at 3, 1. This one was at 0, 2. Its reflection is at 2, 0. This one's at -1, 1. Its reflection is at 1, -1. And that point's not perfect. It actually probably would have been at -2, I bet it was at -7 or something like that. I just tried to show you how it was working. But all you have to do is switch their x's and y's. Let's see, x cubed plus 2. It would have been at -6. But, I mean, it was close. It was close. And I know it's not, maybe it's not mentioned because it's too obvious to a lot of people, but an inverse and its function, if they cross the line of reflection, will always intersect each other on the line of reflection. It'll be the only time where a function is equal to its inverse is when they're on y equals x. This is just a neat thing. Like I said, it's probably not mentioned anywhere because it's obvious. It's neat to say. Questions so far about how to recognize if a mapping is a function or one-to-one, or just these basic ideas with the horizontal line test? None of that's new, right? Okay, great. Awesome. For each of these, what we're going to do is we're going to draw the line y equals x, and I'll draw it as a green dotted line. We're told to sketch the inverse, and then it says, is the function one-to-one? We can answer that is the function one-to-one without doing anything. And that's just by looking to see if the graph passes the horizontal line test. Does this graph pass a horizontal line test? Yeah. Yes, it does. Because this graph passes the horizontal line test, this one is one-to-one. That means its inverse is a function. Does this graph pass the horizontal line test? Nope. This one is not one-to-one. that means its inverse will not be a function. Let's go ahead and throw the line y equals x on here. And unfortunately, this grid is not square, is it? It's rectangular. But let's see, we've got to go through 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. Take some pretty points that you see it has, switch their x and y. So here's a pretty point at -3, -2. Switch that. -3, -2. That's the same words, isn't it? -3, -2. So it needs to be -2, -3. There we go. This is a pretty point at -2, -1. Make it -1, -2, -1, -1, -2. I'm struggling. Here's a pretty point at 1, 0. It becomes 0, 1. And I think this is one at 6, 1. So 1, 6. There you go. What's that blue line look like to you? What if it had a secondary side to it? What's it look like?
Quadratic.
It's half of a quadratic specifically. This is a square root graph. This is half of a quadratic. So square root graphs and quadratics can be inverses of one another. But this is not a whole quadratic, is it? It's specifically half of a quadratic. Here, if I come to this quadratic, when I switch its x's and y's, I'm going to get a picture like that. Which, ooh, Landon says that's 2 square root functions. That's actually the way you have to say it. So a quadratic does not have one inverse. A quadratic has 2 inverses, a positive version and a negative version. This one was more square. There we go. Let's find some x's and y's and switch them. How about the vertex? 0, -2 goes to -2, 0. Looks like I have a pretty point at 1, -1. So that'll be -1, 1. I have a pretty point at 2, 2. Well, the reflection of 2, 2 is still 2, 2. I have a pretty point at 3, 7. So 7, 3. That's enough for me to draw this. Did you notice that I was working on the right side of the quadratic? You could think of the right side of the quadratic being the positive side of the domain. Because you know the domain is all real numbers. It's got a left of the vertex, it's got a right of the vertex, right? Well, as I went to the right side of the domain, it gave me the up side of the graph. And now if I go to the left side of the domain, it's going to give me the downside of the graph. And they are symmetric across this thing's horizontal axis of symmetry. So since I had an orange dot up 1 from the axis of symmetry, I'm going to have an orange dot 1 down. Because I had an orange dot up 2, I'm going to have an orange dot down 2. And because I had an orange dot up 3, I got an orange dot down 3, like that. So yeah, that bottom one does not look good. But there you go. This quadratic, if you wanted to say it had, yeah, it has an inverse, an orange inverse. But the inverse is not a function. If you want the inverses to be functions, you have to have 2 different graphs, a positive square root and a negative square root. So leading back to what I started with when I said I already mentioned inverses, is definition of inverse functions. If f and g are two functions and this happens, if composing them in either order, and actually it's if composing them in both orders, I guess I should say it that way. If composing it f first or g first and they both give you x, then what you can say is f and g are literally canceling each other out, which makes them inverse functions. Just think of a function as nothing but a string of operations. And since operations have inverses, you cancel multiplication with division and cancel squares with square roots. A function is nothing but a whole bunch of operations, and you should be able to undo those operations in a very specific order to undo everything that a function did. So g undoes everything that f did to x in either order. The function g is the inverse of f. Or you can say f is the inverse of g. They're the same statement. So f inverse of x could be put inside of f, or f can be put inside of f of x. Doesn't matter. Either way, f and f inverse cancel each other, leaving you with only x. And here it is. The domain of f is equal to the range of f inverse and vice versa, which we've already said. It says, show that these two are inverses. In order to show that two functions are inverses of one another, you must compose them in both orders, and they have to both give you x. So I'll do f of g of x first. F is 4 times whatever x is. That's where we're going to drop in red g of x. Red g of x, a fraction. Uh-oh, there we go. The fractions in number 1 on that last test seemed to spook a bunch of you. This says divide by 4, this says times 4. Divide by 4 and times 4 are inverse operations. They cancel each other out, giving me x minus 3 plus 3, which is just x. Is it enough to do f of g of x and see that it equals x? No. In order to prove they are inverses, you must be able to do it both directions. Is it possible for one to work and not the other? Yes, it is. So we must check. We've got our function g, and it used to have an x right there. That's where I'll drop blue f of x. These parentheses are not doing anything, so I'll stop writing them. And I'm hoping you could see that this plus 3 and this minus 3 will cancel each other out the moment the parentheses are gone. And I get 4x over 4, which is x. There. It works. Yes, sir.
Couldn't you also do that by like swapping the x and the y around and then just putting y by itself?
So that is algebraically finding an inverse. But yes, and then we're probably going to do that in the next page.
Okay.
Yep. Something that's interesting about functions and their inverses. I already told you they switch the x's and the y's, right? So let's say it's a test, like a multiple choice AP exam question, and it says which of these is the inverse. You know, all you have to do is pick a number for x and plug it in and get its y, and then find out which of the options switches those two numbers. For example, someone give me an x that's not a 0, 1, or a 2. 3. Great. 4 times 3 is 12. 12 plus 3 is 15. So what we now know is that 3 comma 15 is on f of x. If g of x is the inverse, then I can plug in 15 and get back 3. Let's find out. 15 minus 3, that is 12, and 12 divided by 4, is 3. There it is. This is a way of testing if one of the answer choices is the inverse without actually finding the inverse. Does it switch x and y? So why did I tell you to stay away from 0, 1, and 2? Because 0, 1, and 2 do dangerous things. You can't divide by 0, and anything raised to the 0 is 1. 1 squared is 1. 2 plus 2 is 4. 2 times 2 is 4. So you kind of want to stay away from 0s, 1s, and 2s. But powerful test-taking strategy. If you haven't taken the SAT yet, that'll come in handy there too. And somebody used that idea to get number 1 right on that last test. Remember we told you only one person in this classroom got it right? Like 3 people in period 8 got it right, but 1 of them used that strategy. I was very impressed. Test-taking strategy. Hey, look! It's almost like Barry had already flipped it over and knew what was coming. Given a formula for a function, f, here's how you find an inverse. Switch the letters of x and y. Switch the variables. And then get y by itself. Solve for y. Cool beans? Cool beans. Now, here's the thing in parentheses that says, ask yourself, is it necessary to restrict the domain to get a one-to-one version of f? Wonder what that means. We'll find out in the notes. It says, sketch the graph of the function. State its domain and range. We'll find its inverse. We'll sketch the inverse. And I'm going to tell you, we're going to skip part D. Because we already did that. That's just composing them. If you guys don't mind. Verifying inverses means just compose them. We just did that. It's right there. We don't need to do that more. We haven't really graphed square root functions, have we? Strange. Well, here's how you do it. You treat it like it is a quadratic in vertex form. What makes the inside equal 0, comma the number to the far right. It's not a true vertex. It's the starting point, but I'll even cheat and call it a vertex. So -3 comma -2 would be its vertex. Then what is very, yeah, question?
Couldn't you also look at it as a transformation and starts at 0, 0?
Yep. Yeah, and again, we can't really, I can't call it a vertex, but if you can remember back, yeah, the square root function from algebra 2 goes through 1, 1, goes through 4, 2, but yeah, it's just been shifted left 3, down 2. Absolutely. It works all the time as long as you know the parent function. Yep. Transformations work the same for all functions, which is great. Also, because of knowing parent functions and knowing transformations, what would be really great is if you knew that this graph does this. But how did I know that it goes up and to the right? Well, I know what the parent function is shaped like, but also the number in front of x is positive. That tells me my graph points towards the positive x's. The number on the front is positive. That tells me the graph points up towards the positive y's. Yes? If the x was negative, then the graph would be reflected and would point to the left. You're right, you can't take the square root of a negative number, but let's just say it said square root of negative x. If you plug in x equals -1, now it says square root of 1. Which is why it'll point to the negative x's. It'll reflect it over that y-axis. So sketch the graph. Sketch the graph. Okay. I happen to know that this graph is going to go here. Because if you use x equals -2, you get -2 plus 3, which is 1. Square root of 1 is 1, and 1 minus 2 is -1. I also happen to know that if I use x equals 1, I'll have square root of 4. So my next pretty points at x equals 1. Square root of 4 is 2, and 2 minus 2 is 0. 1 comma 0. And the next pretty, what's the next perfect square after 4? 9. So what makes this equal 9? X equals 6, which is not on the grid. Okay, so that's all we have that's actually on the grid. Like that. So what is its domain and range? Its domain is all numbers to the right of -3, including -3. What's its range? Smallest y value is -2, including -2. And then points up. There's its range. Let's sketch the inverse. Oh, it says find the inverse, state the domain of the inverse as well. So before I sketch the inverse, which is just going to be me switching x and y, let me go ahead and switch x and y and get y by itself. So here's us finding the inverse. X equals square root of y plus 3 minus 2. Our job is to get y alone. And once y is alone, we'll call it f inverse. Okay? Because does this graph pass the horizontal line test?
Yeah.
Yes, it does. That means its inverse is a function as well. So this is 1 to 1. Its inverse will be a function. What do I need to do first to get y by itself? Add 2, good. Add 2 to both sides. Okay, we are well on our way to have y being all alone. What's got to go next? Got to square both sides, yeah. We have to get rid of that square root, so we have to do this. And then I hope it's obvious the last thing I need to do is subtract 3 from both sides. And I'm not going to say y equals, I'm going to say f inverse. Here we have a problem. This is a U-shaped graph. But I cannot draw a U-shaped graph. Because in order to sketch this thing's inverse, I have to switch its x's and y's. Let's sketch its inverse and then talk about this. Let's take this thing's wannabe vertex at -3, -2, swap those two. -2, -3. Oh, that would have been the vertex of this quadratic. How about that? Here's one at -2, 1. Excuse me, -2, -1. Becomes -1, -2. Here is one at 1, 0. Becomes 0, 1. That is precisely half of a quadratic. Go home, quadratic, you're drunk. I missed that dot. But you could see it's the right side of the quadratic. Its domain is all the numbers to the right of the vertex. Its range is all the numbers above the vertex. Look at that. The domain and the range have switched places. This is one of those kinds of graphs where you must restrict the domain in order for your function and their inverses to be true inverses of one another. If I had not written this, and instead I just wrote that, this is not the inverse of this square root graph. Because this is a U-shaped graph, and this is not a sideways U-shaped graph. It's only half. What that means is, anytime you're dealing with a quadratic and a square root graph, or a quadratic and a square root function, and I don't care which one is the function, which one's the inverse, it doesn't matter. You must restrict the domain of the quadratic. Always. You're cutting it in half. So I guess the real question is, how do you know which half to use without graphing? The answer is transformations. The domain of the quadratic and this what I'm saying right now is only for inverse situations. The domain of the quadratic is the range of the root. So you look at your square root function, you determine where its faux or fake vertex would have been. This will always be the y value of the vertex out here. And then you ask yourself, does the graph point up or down? This graph points up. That means I know this is the smallest y value. This thing's range is -2 to infinity, meaning this thing's domain had to be -2 to infinity. And if there had been a minus sign on the outside, then I would have known that this was the top of the range because the graph points down. So either down up to -2 or up away from -2. And that will always work when you're talking about quadratics and roots being inverses of one another. It's just a little domain trick that uses transformations. Now this one, boop, this is a cubic function. Excuse me, cube root function, sorry. Cubics look like this. And you remember back to our polynomial chapter, it could have more wiggles to it, right? But not if you're going to write it in what you could call inflection point form. We're used to calling a vertex form of a quadratic, but cubics and cube roots, they don't have vertices, they have inflection points. So when written like this, you could see the point where the graph is centered around. So this is a cubic, this is a cube root. Hold on, I just drew that wrong. Sorry, scratch that idea. There we go. This thing's inflection point is what makes the inside equal 0, comma the number to the far right. And now you just want to be able to take cube roots of numbers. The first thing that we could take the cube root of is 1. So what would I have to plug in here to get a 1 on the inside? Trying to get a 1 here, folks. What would I have to plug in? No, what number would have to go right here so that this equals 1? -1. If I use x equals -1, I get -1 plus 2, which is 1. So at -1, I have a pretty point. I have a perfect cube. At -1, I get this cube root of 1, which is 1, minus 1, which is 0. -1, 0. The next perfect cube after 1 is 8. So what x value would I have to plug in to get an 8 underneath this radical? 6. Ah, once again, we needed x equals 6, and it is not on our picture. Shucks. Oh well. It's okay. Not a big deal. That means we're done going to the right. It's going to look, by the way, if we had 6, we would have had cube root of 8, which is 2. 2 minus 1 is 1. So the next one would have been at 6, 1. And it's an inflection point. So instead of going from the vertex, instead of going from the inflection point and going up 1, right 1, I'm going to go down 1, left 1. And it's just going to do that. Is this graph 1-to-1?
Yeah.
Yes. This is a function, and it passes the horizontal line test, so its inverse is a function. Its domain and range is actually very easy. All real numbers for both. That's true for every cubic and every cube root. All real numbers for both. Let us switch x and y. X equals cube root of y plus 2 minus 1. Now it's just like the other one. Add 1 to both sides. Raise both sides to the third power. And subtract 2. Because this graph passes the horizontal line test, I know its inverse is a function, so I'll write g inverse of x when I subtract 2. I'll get g inverse of x equals x plus 1 cubed minus 2. Its inflection point is what makes the inside equal 0, comma the number to the far right. -1, -2, which is not surprising because you're supposed to switch the x and the y. This dot, which was at -1, 0, is at 0, -1. And this dot, which was at -3, -2, is at -2, -3. There it is. And if you turn it sideways, you can see, yeah, those graphs are pretty much reflections of one another. Right down the line, y equals x. I think that's it for today. Feel good? We good? Great. Appreciate you, nerds.